So now that we have a pretty decent understanding of the equilibrium state, what we're going to do is we're going to go and finish off chapter 16, and in particular we're going to finish off section 16.4, where we look at how the Gibbs free energy and the equilibrium constant are related. This will also give us a little bit of a chance to explore how the equilibrium constant is affected by changes in temperature. So we already know that from chemistry 162 that if delta G is less than 0, then a reaction will spontaneously proceed to the right. So if we take methane and we burn it in the presence of oxygen, we know that methane burns in oxygen to make CO2 and water vapor, and delta G is less than 0. From that, what we also know is that if we take that reverse reaction, when we reverse the direction of a reaction, we reverse the sign of delta G, that when we combine water vapor with carbon dioxide, it doesn't spontaneously make methane and oxygen. So the question now becomes are there any other ways that we can know that a reaction will proceed spontaneously towards products? And we do, right? If Q is less than K, a reaction will proceed spontaneously to the right. And similarly, if Q is greater than K, a reaction will proceed spontaneously to the left. So if Q is less than K, another way of saying that is that delta G is less than 0. And if Q is greater than K, another way of saying that is that delta G is greater than 0. So Q and delta G should be able to be related in some way. So a reaction will proceed spontaneously until delta G equals 0, and at that point there will be no net movement either towards products or reactants. So is there another way of saying that there's no net movement of a reaction towards products or reactants? Of course there is, right? When Q equals K, we see the same effect as when delta G is equal to 0. They are the same things. So when delta G equals 0, our system is at equilibrium, or alternatively, when Q is equal to K, we're also at equilibrium. So really what we're saying here is that both Q and delta G are measures of how far a system is from equilibrium. The more negative a delta G, the greater propensity for the reaction to proceed towards the right. The smaller Q is compared to K, the greater tendency for that reaction to proceed towards products. So they're both measuring the same thing, and what they're measuring is how far away is your system from equilibrium. So because they're measuring the same thing, people want to set out about to find a relationship that relates the two. And here it is. It says that delta G is equal to delta G naught, the standard Gibbs free energy change, plus RT log Q. So Q being our reaction quotient, RT being the ideal gas constant, and the temperature in Kelvin. So delta G naught is the free energy change under standard conditions for our reaction, and typically how we calculate that is by using the Hess's law in combination with the values that are found in the back of the book, and we just do the sum of the delta G's of the products minus the sum of the delta G's of formations of the reactants to get the delta G naught for our reaction. Now it's interesting to think about what happens when Q is equal to K. So when Q is equal to K, the system is at equilibrium, and when the system is at equilibrium, not only will Q equal K, but delta G will be equal to 0. So we can substitute these two expressions into our expression for delta G, and what do we get? So delta G is equal to 0, Q is equal to K, so 0 is equal to delta G naught plus RT log K, or reorganizing delta G naught equals minus RT log K. So if you have delta G, you can always get K, and if you have K, you can always get delta G naught. So we can interconvert between the two. So here we go. It says use the following data to calculate Kp for the reaction, and it gives you the reaction here at 298 K. So this is the reaction that we're trying to calculate Kp for, and then they've given two other reactions here. And if you look at this, the reaction that we're interested in is the sum of those two that follow there. So here it is here, and then we've got the delta G naught for these two. So when I add reactions together, I add their delta G naughts, so I can get my delta G naught for the overall process, which is what I've done here, right? 173.2 plus minus 69.7 gives me the delta G naught for this overall process. Once I've got the delta G naught, I can use my little formula here and I can turn it into a K. Now this is a very big positive delta G naught. So delta G naught here is greater than 0. So what that tells me is that this reaction is going to favor the left-hand side. It doesn't really produce minimal products. It's a non-spontaneous reaction because this is a positive number. So I'd be expecting a very, very small K, and I got a very small K, 10 to the minus 19. A few things to be aware of when you're using this formula here. The delta G's will be given to you normally in kilojoules per mole, but you'll need to convert them to joules, which is what I've done there. And then the R value, we want to be using the R that has joules in its units, so it's 8.314 joules per mole per degree Kelvin. And also make sure that your temperature is in Kelvin as well. So you just really got to keep track of your units when you organize this. Of course, you can use the solver if you don't want to do algebra and reorganize. So in the Le Chatelier's principal lab, we saw qualitatively that K is dependent on temperature. So if we have the cobalt hexaaqua cation, and it is pink, and then we add some heat, it will get converted to the cobalt tetrachloro anion, which is blue in color. And we can move this equilibrium backwards and forwards. If I add heat here, it'll move it over to the blue side. If I take heat away, it'll move it over to the pink side. So we can see that here it is, we've taken heat away, it shifts towards the pink. Here we add a bunch of heat, we elevate the temperature, it shifts to the right, it turns blue. So the value of K is clearly just on the basis of these observations dependent on T. The question is, though, this is qualitative, right? Is there a way of calculating K at different temperatures, i.e. what is the numerical relationship between temperature and the reaction and the equilibrium constant? So we did learn in chemistry 2 that delta H, delta S, delta G, and T are related like so. So delta G naught equals delta H naught minus T delta S, very famous equation. And we've also just learned that you can express delta G naught in terms of K. So what I can do is I can take my expression for delta G naught and I can put it up there, right? So that's what we've done here. Okay, so what we want to do now is we just want to have like the log K term on one side, so I'm going to divide both sides by minus RT, which is what I've got here. And if you look here, this is of the form y equals AX plus B, where y is log K, your A is, and X is 1 on T, your A is minus delta H on R, and your B, which is your intercept, is going to be your delta S on R. So, there we go. So what we're really saying is, if you plot log K against 1 on T, you're going to get a straight line. It's going to have slope minus delta H on R, and intercept delta S on R. And so this is a really useful tool. This is very, very useful. We are assuming that delta H and delta S vary very little with temperature, which is mostly accurate most of the time. So, the linear form of equation is useful if you have many points and you want to make a graph and go through all of that effort. But for simple calculations, it's often more useful to have what we call the 2-point form of an equation. And we've done this previously with the Arrhenius equation. And so I won't bore you with the math to get to the 2-point form, but we can organize a 2-point form of it where we have log K1 on K2 equals minus delta H on R multiplied by 1 on T1 minus 1 on T2. And this 2-point form of this equation is called the Van Hoff equation. And you can see it looks a lot like the Arrhenius equation, and it also looks a lot like the Clausius-Clapeyron equation that we had earlier in the sequences. So it turns out that the reason why it looks like the Clausius-Clapeyron equation is because the Clausius-Clapeyron equation is just really a particular example of the Van Hoff relationship. So the Clausius-Clapeyron equation is concerned with the vapor pressure of a liquid in equilibrium with its gas. So we have a liquid in equilibrium with its gas with a particular enthalpy of vaporization. The equilibrium constant for this process is just going to be equal to, particularly as expressed as Kp, is just going to be equal to the partial pressure of the gas, because we don't include liquids in our expression for equilibrium constants. So here's our Van Hoff equation. It says log K1 on K2 is equal to minus delta H on R multiplied by 1 on T1 minus 1 on T2. But for a liquid in equilibrium with its vapor, the K is just equal to the pressure of the vapor, and the enthalpy of the reaction is just equal to the enthalpy of vaporization. So you put those back up into your Van Hoff equation, and what do you end up with? You end up with the Clausius-Clapeyron equation. So they're really the same thing. Okay, so here's an example problem. It says at 600 K for the following reaction, Kc equals 1.7 by 10 to the 8. So what that's really telling you is it definitely favors the right-hand side. This reaction, I would imagine, is going to be almost all products at this particular temperature. 1.7 by 10 to the 8 is a big number. So it says an engineer places 0.04 moles of SO2 and 0.028 moles of O2 in a 1 litre container. So these are really just moles per litre, aren't they? Because it's in a 1 litre container. And raises the temperature to 1000 Kelvin. You want to be careful there. That's a different temperature for what we were given the original K for. And then it says at equilibrium, 0.002 moles of SO3 is present. Interesting. So this gets complicated. And then it says calculate delta H for this reaction. So let's set up the ice table for the 1000 K example. We're working in concentrations, so we're going to put moles per litre there. And here's our equation, initial change equilibrium. And so to begin with, we just have all reactants, 0.004 moles per litre SO2, 0.0028 moles per litre O2, and no product. And then we wait, it comes into equilibrium. So what's going to happen? Well, this guy, it's going to go to the right. It has to, because we've got 0 products. This is going to decrease in concentration by 2x. This will decrease in concentration by 1x. And this will increase in concentration by 2x. So at equilibrium, what we know it says is that 0.02 moles of SO3 is present. So what that tells you is that 2x is equal to 0.020. So therefore x is equal to 0.010. So I've kind of did the math for that down here. And then that allows me to calculate values in here and in here for, I should have just made that a 7, shouldn't I? There we go. But it doesn't matter. And then that's just going to be 0.0020 that was given to us. Okay. All right. So here are our equilibrium values. Everything correctly updated there. Whoa. So everything correctly updated here. This is correct. I was just kind of doubting myself. And so now I can go ahead and calculate Kc at my higher temperature at that 1000 degrees. So products over reactants, but I've got to square the SO3 and I've got to square the SO2. They are. So put my equilibrium values in and I get an equilibrium constant 556. So at the higher temperature, at T2, K2 was a lot lower. Okay, so we want to be thinking about that. Raising the temperature caused it to move to the left. So I'm thinking that this guy makes heat. Okay, so I got my second K. So I want to solve for the enthalpy, right? So here's my Van Hoff equation. I had 1,000. And then I had my other temperature 600. It doesn't really matter what one I put where. But I've got two temperatures, 1,000 and 600, and I've got my two Ks. Okay, so I reorganize this guy to solve for delta H. So I'm going to bring minus R over there, and then I'm going to divide the whole thing by 1 on T1 minus 1 on T2. So I've just got to kind of keep things straight. I've got to make sure my K1 goes with my T1, my K2 goes with my T2, and then my temperatures need to be in Kelvin, and my R needs to be in units of joules per mole per degree Kelvin, or it's not going to work out. So I put all of that in, and this is going to return my delta H in joules. Okay, so minus 1.58 by 10 to the 5, or a minus 158 kilojoules. You can use the solver directly here to solve for delta H if you want to use the solver and avoid the algebra. So this reaction is exothermic, right? It releases 158 kilojoules of heat. And so that makes sense that heat is a product because as you raise the temperature, K went down. So when the temperature went up, we added heat, and that pushed the equilibrium to the left, and K got smaller. So at T2, the temperature went up, K2 went down.